You know, every network engineer has this amazing toolkit full of these super smart automated power tools. But sometimes you just need a good old-fashioned hand tool for a precision job. That's exactly what IP static routing is. It's the tool you grab when you need absolute hands-on control over where your data goes. So let's dive in and see why this manual tool is still so incredibly important.
Okay, but that immediately brings up a huge question, right? I mean, we've got these incredible dynamic protocols, things like OSPF, that basically do all the work for us. They figure everything out, they adapt when things break automatically. So why on earth would you ever go back and manually configure a path? It feels a little outdated, doesn't it? Well, as you're about to see, there's some really compelling reasons.
All right, so let's make the case for going manual, because it turns out there are some big-time advantages to static routes, especially in situations where you need precision more than you need automation.
You can really think of this as a tale of two different philosophies. On one hand, you've got static routing. It gives you explicit, totally predictable control. You tell it the path, and that is the only path it will use. End of story. It's super simple and has basically zero overhead on your router's CPU. The catch? If something in the network changes, you're the one who has to go in and manually update it. Dynamic routing, on the other hand, is the complete opposite. It's smart, it's adaptive, it's automated, but all that brainpower comes at a cost. It's more complex and eats up more CPU and bandwidth.
So the real trick is knowing when to pull this manual tool out of the bag. They're absolutely perfect for small, simple networks. We call these stub networks. Just picture a small branch office that only has one single way out to the internet. Why would you bother setting up a complex routing protocol when a single simple command does the job? They're also a huge deal for security. Imagine you need to force traffic to a specific server to always go through a firewall, no exceptions. A static route does that, even if a technically shorter path is available. And, as we're going to see in a bit, they are an amazing way to build backup routes.
Okay, so let's get into the nuts and bolts. We're going to start with the everyday tool, the most common type you'll ever configure, the standard static route. And what's interesting is that there are actually 3 different ways you can tell a router how to get a packet where it needs to go. Yeah, you can really think of it like giving different levels of directions. The first way is just telling the router who to hand the packet to next, the IP address of the next router. The second way is to tell it which door to shove the packet out of, which physical interface to use. And the third way, for when you want to be super clear, is to tell it both the door and who's on the other side. And each of these methods has a time and a place. So method 1 is the most common by far, the next hop route. You're basically just telling the router, hey, to get to this network, just give the packet to this neighbor at this IP address. The router takes it from there and figures out the rest. Now, the second method seems simpler on the surface, but it's also way less specific. Instead of naming the neighbor's IP, you just tell your router, for this destination, just push the packet out this physical port. It's easy, sure, but that simplicity comes with a pretty big catch. And this is where you really need to pay attention. This whole just push it out the door method, it's really only recommended for true point-to-point links, like an old serial interface, where there's literally only one other device at the other end. If you try this on a multi-access network like Ethernet, where you could have dozens of devices, it gets messy. The router has to stop and basically shout out using a protocol called ARP, asking, hey, who's supposed to get this? And that shouting match creates a ton of extra traffic and processing that you just don't need. It's super inefficient. And that brings us to the perfect solution for networks like Ethernet, the fully specified route. This is the leave no doubt method. You tell the router both which door to use, the exit interface, and exactly who to give the packet to, the next hop IP address. You're leaving nothing to chance, which is exactly what you want when there are multiple devices hanging around. Okay, so this whole idea of being super precise, it goes from best practice to absolutely mandatory when we start talking about IPv6 and its link local addresses. You've seen these before, the ones that start with FE80. You gotta remember, these addresses are special. They're not meant to be unique across the whole internet. They're only guaranteed to be unique on a single wire, on a single network link. And because of that, because they're not globally unique, if you use a link local address as your next hop, you have to use a fully specified route. It's not optional. Just think about it for a second. Your router could have a neighbor with the address FE800000000001 connected to its first Ethernet port, and another totally different device with the exact same address connected to its second port. If you just tell the router send it to FE8000000001, how is it supposed to know which one you mean? It can't. By specifying the exit interface, you're telling it which FE80000000 you're talking about. You remove all the guesswork.
All right, we've covered the everyday screwdrivers and wrenches. Now let's dig a little deeper into the toolkit for some more specialized gear. We're going to look at two really powerful tools, default routes and floating routes. And each one is designed for a very specific, very cool job. First up is the ultimate wild card, the default route. You'll often hear this called the gateway of last resort. It's a static route that is basically a catch-all. It matches everything. For IPv4, it's that famous quad 0 route. And for IPv6, it's the double:/0. What these both say is, look, if you've checked all your other routes and you have no idea where this packet is supposed to go, just send it here. It's the classic route you point at your ISP to get out to the internet. Next up is one of my favorite tricks, the floating static route. This is just a brilliant way to create a backup path. At its heart, it's a completely normal static route, but with one little twist. You intentionally make it seem less trustworthy. You do this by manually giving it a higher administrative distance, or AD. So let's walk through how this works. Picture your network. Everything is running perfectly. You have your main static route to the internet. By default, a static route has an administrative distance of 1, which is basically the best score you can get. It's super trustworthy. So all your traffic is happily flowing along this primary path. But in the background, you've also configured a second static route. This is your floating route. It points out a different backup connection. The key is you've manually set its administrative distance to something higher, like 5. Now, because 5 is a worse score than 1, the router looks at it and says, that's not as good. So it doesn't actually put it into the main routing table. It just keeps it on the bench, waiting in the wings. And then it happens. Your main internet connection goes down. That super trustworthy route with an AD of 1, poof, it's gone from the routing table. The router immediately panics for a split second and says, okay, what's my next best option? And guess what's waiting? Your floating route with its AD of 5. Suddenly, it's the best path the router knows about, so it instantly installs it and your traffic switches over to the backup link, hopefully before anyone even notices.
Okay, for our last section, we're pulling out the most precise instrument we have, kind of like a network scalpel. It's called a host route. And after that, we'll cover what is maybe the most important step of all, verifying your work to make sure you actually did what you thought you did.
So, a host route is exactly what it sounds like. It's a route to a single host, a single IP address, not a whole network. It's the most specific you can possibly get. For IPv4, you do this with the ultimate subnet mask, a /32. A /32 mask basically tells the router, I am not kidding, every single one of these 32 bits has to match perfectly, no wiggle room. And the idea is exactly the same for IPv6, just with a much bigger number, obviously. It's a /128. This creates a route that is just laser-focused on one specific device. It's the perfect tool if you need to lock down the exact path to one super critical server. Of course, no network change is complete until you prove it works. You can't just type the command and walk away. You'll want to use commands like show IP route static to make sure your route actually made it into the routing table, and maybe check your running config to make sure you didn't have a typo. But the real proof is in the pudding, right? You got to ping to make sure you can actually reach the destination, and then use traceroute to prove that your traffic is taking the exact path you wanted it to take. So as you can see, static routes are absolutely essential tools for precision and control. But the real magic, their true power, happens when you start blending them with the automated, dynamic world. So I'll leave you with a final thought to chew on. How could you use what we just talked about, a floating static host route, to create a super specific backup path for one single critical server, even if the rest of your network is running something dynamic like OSPF? It's that kind of creative mix of manual precision and automated power that really separates a good network design from a great one.